Can you hear me?
Yes.
Yeah, okay, super. So, great. Welcome to the class. Here is the plan for the next 2 weeks. We finished talking about the high-dimensional data. So what we are going to do in the next couple of weeks is talk about graph-structured data. So basically, data that can naturally be represented as graphs. And we will talk today about computing importances of nodes in large graphs and how these algorithms have been developed and what can we use them for. So that's the idea. And basically what this will allow us to do, it will allow us to measure similarities between the nodes in the graph. And we'll get to that. So what do I mean by graph structured data? There is amazing amount of different types of data that can naturally be represented as graphs. Graphs meaning a set of nodes and a set of edges or connections, links between these nodes. If you think about representing social networks, then you can think of social networks as graphs of people and people having relationships with one another. And of course, these relationships can be heterogeneous in a sense that we can have multiple types of relationships, from friend to relative and so on, co-worker and so on. Another case where analysis of networks is amazingly important is if you want to understand the media ecosystem. If you want to understand polarization, opinion formation, and things like that, then networks are an example of this. What is this? This is a visualization of United States political blogs and how they link to each other. And the blogs are colored based on political affiliation. And you can see this nice but worrying separation between the two sides, the red and blue, right? You can also think of, if you think of science, science is naturally a network. One way how we can create networks out of science is that we look how scientists cite each other. So you can start asking, how do different fields of science, how do they relate to each other? And this is one such visualization that tries to say, how do different fields fit together? And you can see that, for example, computer science and, computer science here, right? You see what are the relevant areas. It's kind of math and physics. Then it's, the chemical engineering and things like that. And then on this side should be kind of social sciences and so on. So this is a picture that wraps around. But it nicely says what computer science is all about and what does it, like what connections does it have in terms of applications and so on, right? So this is naturally a network. Another case where networks are amazingly important is if you think about communication infrastructure. Again, that communication infrastructure can be modeled as a graph. And of course, here is the oldest kind of networks problem, from 1700 by Euler, who was wondering how to traverse over all these bridges and get back to the same place and traverse each bridge only once. But the point is that this is a technological network. It's a network describing human infrastructure. So you can think about describing roads, maps, water distribution network, electrical grids, with networks, and then thinking about how do you do optimization, robustness, and things like that over them. So basically, my point is that graphs are everywhere, and you don't have to look too hard to find them. And what I want to talk to you today about is actually thinking of the web as a graph. And the way you can think of the web as a graph is that you think of nodes as web pages and edges as hyperlinks, right? So if I would have my class on social networks here, then the way I would create a graph of this is that every page is a node and then links point to other pages. So this creates connections, in this case, directed connections between the nodes, right? And here is one example, but you can imagine the web being this massive network of web pages pointing to one another. Of course, with the emergence of sites like Facebook and so on, when everything is machine automatically generated, they don't necessarily conform to this static view of the web. But if you think of static web pages, then this is and most of the web is still static. This is a good analogy of how to think about the web as a graph structure. So then if you say, I have this graph of the web, the question is, how do I go and organize, or how is this graph organized? How can I understand what are, let's say, important nodes in this graph? And if you want to go and organize the web, then the first try to organize the web was a human curated way to organize the web. And then there was this thing that now unfortunately is the history, but actually we are right, that essentially the way Yahoo started was that they had these human editors who will go and classify web pages into different categories. So if you wanted to find a web page, the idea was that you would go here and say, oh, I'm interested in health, and you would click and then find a list of health-related web pages, right? And you know, people tried to do that until kind of Google came and said, web search is the right way to do it, right? That, you know, rather than trying to organize the entire web in these human curated categories, let's come up with a search bar that will allow us to search documents. And there is a very big field that worries about how do you search documents, and that field is called information retrieval. And information retrieval is older than the web is, but information retrieval really worried about, oh, you have a set of 10,000 news articles trusted, you want to search over them. Or you have a set of, I don't know, 1,000 documents, you want to search over them, right? Like patents, articles, so on, right? But the difference becomes that web is this huge piece of content, lots of untrusted adversarial things, lots of spam. So how do you now search over this untrusted set of documents? And this is kind of what we'll talk about, right? So really, if you want to search the web, you have two problems, right? First is that that web contains many different websites. You know, who of them should you trust, right? How would you compute the trustworthiness of each page? And how would you say this is a good part of the web and this is untrustworthy part of the web? And then the second thing is, you know, you could ask, how do I find the best answer to the query newspaper? And if you think about this, maybe, you know, there is no singular right answer to the query newspaper, and maybe even the newspaper word won't appear on the best newspapers, right? I don't think a word newspaper appears on New York Times or Washington Post, right? So how do you search for newspapers? So the idea is that, you know, that you may want to go and exploit the web graph structure to allow you to find answers to queries like that. So that's why graphs are important. So what we want to do today is take this abstract problem where the idea is I have a graph, let's say a graph of the web, and I want to understand how important is a given node in the graph, right? How important is a given node? So maybe, you know, blue node versus the red node. I would kind of say that blue node seems more important. You know, it has maybe more links and so on, right? So the question is, how would I compute the importance of the node in a graph? That's what we want to do. And really, the research area that tries to deal with this is called link analysis. It's basically, the idea is I want to analyze the links of a graph so that I can understand the graph better. I can understand which nodes in the graph are important. And today we will talk about PageRank, which is the main method in this area. And then we will talk about certain extensions and applications to web spam on Thursday. So that's kind of the plan for this week. So what I want to do is I want to talk to you about PageRank algorithm that was essentially that was invented by Larry and Sergey when they went and founded Google. So PageRank was or is one of the secret sauces of why Google was able to become the dominant search engine. And the reason for that was they realized that web is a graph, that web is a connected set of documents, and that these connections can allow you to much better know how to search over the web than think of web as an isolated set of, you know, independent documents where you can only do text retrieval. So PageRank was one of the core algorithms, and it was developed here at Stanford as a part of the project that gave rise to Google. And there is a paper actually that Larry Page and Sergey Brin are the authors on PageRank. You can find it, and I think the title is PageRank: Bringing Order to the Web. So the idea is the following, right? What do we want to do? We want to figure out how important is a page, how important is a node in the graph. Because, right, when we return search results, maybe we will just look at the query, look at what are all the pages that match that query, but then we will sort them by their importance in the graph, right? So this importance will give us kind of a priori believe or score how important is the page, how good is the page if we don't even know the query yet. Okay? So one way you could do this is to say, I will count the number of links a page has. The first idea would be, let me count the number of outlinks. And if you would do that, then pages that are huge and have lots of outlinks would win. So you don't want to do that. Then, you know, what you could do is to say, I will count inlinks, because inlinks are harder to fake. You have to find other people on the web who will point at you. So you could look at the inlinks and say, this is how important is a given page. But then you quickly realize that not all inlinks are equally important, right? Like you would say, links from important pages make you more important, right? So it's not about the total, I don't know, number of friends you have, but it's about how important are those friends, and they give you importance, right? But of course, those friends' importance also depends on their friends' importance. So we have this kind of recursive definition where my importance depends on my friends' importances, and my friends' importances, again, depend on their friends. It kind of never ends. And this is how PageRank will be computed, and why we call it, it's a recursive type of question. Okay? So another idea you could think of this is this formulation of what is called a RandomSurfer. And I will introduce these concepts now and make them more precise later, but hopefully this will kind of give you some intuition that will follow us through. So one way you could compute the importance of a page on the web page on the graph is to say how many people visit that page. Okay? And the more people visit the page, obviously the more important is the page. But you cannot watch everyone spy on them to see what pages they go and visit, right? So what could you do is to say, let's come up with a model of how people browse the web. And maybe one possible model how people browse the web is called the RandomSurfer model. And the RandomSurfer model is a person who, you know, gets to a page, clicks a random link, gets to the next page, clicks a random link, and keeps walking around the web. Right? They are called RandomSurfer because they are surfing the web, but in this random way. Okay? So you can think of this RandomSurfer as a very naive model of how people would browse the web. Right? Where the idea is that this RandomSurfer starts at a random page and then, you know, follows an outlink from that page, arrives to the next page, follows another random outlink, and this process continues. And what is PageRank? PageRank is something we will call limiting probability of the surfer being at a given page. So the idea is that the surfer walks very, very long time, you stop the clock, and you ask, where is the surfer? And the PageRank is the probability distribution over where the surfer might be at that time when you stop the clock. Okay, so the surfer walking around creates some distribution over the probability of the surfer visiting that page, and PageRank is that probability. Okay? And the idea is, as I mentioned before, is that this PageRank score will become to be this kind of recursive question, where we'll say the importance of the page is some kind of combination of importances coming from its neighbors. Or you could say probability that the surfer is at a given page is the probability that the surfer was at some nearby page and then navigated to that page itself. Even more cool stuff will happen. It will turn out that this PageRank score will become some eigenvector of some funny transition matrix. Okay, so it's a lot of beautiful things happening, right? I told you about the recursive definition, I told you about the RandomSurfer model, and now I started mentioning some eigenvectors and eigenvalues, and it will turn out that all this kind of magically comes together in this great symphony. Okay, so that's the preview. So we'll talk about the RandomSurfer model, recursive formulation of PageRank, and then it will turn out that this is some eigenvalue problem that we can solve very efficiently. So a lot of cool stuff, a lot of cool mathematics will kind of coalesce in this beautiful symphony. Okay, how would the PageRank scores look like on a real graph? Here is a real graph where the size of the circle or the number is proportional to the PageRank score of the node. And the PageRank scores here, I made them to sum to 100. I want to make you some observations, right? For example, node B has a lot of importance because of lots of other nodes point to it. Makes sense, right? notice that node C has also huge importance. And the reason why it has so huge importance is because this node B that is very important is the only node that points to it. So it makes sense for this node C to be high importance as well, right? You can, for example, notice that, these nodes here who nobody points to have low importance, right? You also notice, for example, that, if you compute, if you say, how about E and F, E has 3 nodes pointing to it, F has 2 nodes pointing to it, so E is more important than F, right? So, for example, D has E pointing to it, so D is more important than these little guys, but it's less important than E because nobody else points to the D itself as well. And then, D kind of points to A and B, right? But if you look at this and compare these sizes or these numbers, it kind of makes a lot of sense for B to be the most important. The reason for C being important because they have this very important friend B. These ones, nobody's pointing to them, so they have very little importance, and so on and so forth. Okay, so that's what this will allow us to do, and will allow kind of to get this intuition and mathematically formulate it. So here is now the recursive formulation of the PageRank problem, right? How do we think about it? We say that every link's vote, the weight of the vote of the link, is proportional to the importance of the source web page. So the idea is if page J has some importance R sub J, right, and it has n outlinks, then that page takes its own importance and splits it n different ways equally, okay? And then, right, like if the page J says what is my own importance, page J simply takes the importances from the pages that point to it and sums them up, right? So the idea is if I'm page J, my importance is 1/3 of the importance of page I and 1/4 of importance of page K. Why 1/4? Because page K has 4 outlinks. So whatever is the importance of K, J gets 1/4 of it. Whatever is the importance of page I, because I has 3 outlinks, 1/3 of it J gets, and that is J's importance. And of course, when J now propagates its importance further, J has 3 outlinks, so each of the neighbors gets 1/3 of the J's importance. Okay? So that's what do we mean by a recursive definition, where you collect importances from your friends and send them to people that you point to, and you split it equally across the outlinks. That is essentially what is called the flow formulation. The reason we call it the flow formulation because we can think of the influence flowing over these edges, right? Whatever is your influence score, you give 1/3 of it to every of the people who are downstream for you. Okay? So now I give you the first example. Here is my graph of the web from 1800 when the web was very small, and I have these 3 different websites and how they link to each other, right? And the way you can think of this is now to say node A gives half of its importance to node M and the other half of its importance to node Y. And then node Y has a self loop, so half of the importance of Y stays with itself and the other half is sent to node A, right? And the way you can now think of this is that, that the vote from an important page is worth more, and that a page is important if it's pointed to by other important pages, okay? So I can define the rank, the PageRank score, R sub J of some page J as simply the sum over the importances of the pages that point to J, where every importance is divided by the degree of J, of the degree of I, right? This is exactly what I had on the previous slide. I say my importance is the sum of importances of the people that point to me, and each one of them gives me 1 over the degree of their importance, right? So I'm summing from people that point to me, and their importances are equally split among their outlinks. And this is what I have, okay? So now if I would write out, here are what is called the flow equations, right? I say, what is the importance of M? Importance of M is half importance of A. So here's the equation for M. equation for A says importance of A is importance of M plus half the importance of Y, right? So importance of A is half importance of Y plus importance of M. And then what's the importance of Y? Importance of Y is 1/2 of importance of Y. That's the self loop plus the in-link from node A. So it's half of the importance from A. Where did I get this 1/2? Because nodes have 2 outlinks, right? This is the number of outlinks of a given node. Okay? So now I have this set of equations. So what could you do? You could say, haha, I have 3 equations, 3 unknowns. I'm good to go, right? You could say, oh, there is no unique solution. But basically, with 3 unknowns and 3 equations, what you get is you get multiple different solutions, but they're just scaled versions of one another. So if you say my PageRank scores will sum to 100, now you get the 4th equation. You have 3 unknowns, 4 equations. You can go solve the system, and here are your importances. Okay, so here I said they have to sum to 1. So here are the importances of pages. And this sounds great, right? I could use Gaussian elimination and do this. It turns out that this is a very bad idea. It's kind of computationally too expensive to do this, so nobody does this. So let's try to find a new equivalent formulation that won't require this recursive equation solving. Okay, so that's the next step. Do people have any questions? Okay, so what we learned so far is this recursive definition where the importance of the node depends on the importances of the nodes that point to it. And that defines a system of equations that's up here that you could solve, and if you solve, this would be the solution. But solving that system is too expensive. You want to do this for the whole web graph with, I don't know, billions, trillions of pages. So you need something else. So here is how we will do this. We will go and define what is called stochastic adjacency matrix M, where what we will do is the following. If page I has this sub-I outlinks, then if I points to J, then the entry MJI equals 1/di. Okay, and otherwise is 0. So essentially what this means is that our M is column stochastic. It means every column will sum to 1. Okay, that's why will it sum to 1? Because every entry, every node I has D outlinks. So if I sum over the column, it means that I'm summing 1/d times, which equals 1. So that's why this will be column stochastic matrix, right? And then I will define what is called a rank vector R, where vector will have 1 entry per page, 1 dimension per page, and that, the ith component of vector R will be the PageRank score or the importance score of that page I. And I will require that these scores sum up to 1, so that they are a probability distribution over the nodes. That's another way to look at it, okay? And then it turns out that my flow equations from the previous slide can be rewritten as R equals M times R, okay? Why is that the case? Here are my previous flow equations that we like and we know. And if you look at it, what is this saying? It's saying entry for node R is all the nodes I that point to it, importance of the node I multiplied by 1/degree of I, right? In the M matrix up here, we store 1/degree of I. So what we are doing here is just saying R, right? The new R equals the old R summed up and multiplied by 1/d. So this in matrix notation is that, okay? And now you can start seeing that this looks like an eigenvalue problem, right? Like lambda x equals A times x. So it looks quite similar to that, okay? So just to give you a more proper example, right? I have the flow equations up there. I showed you that this equation that M times R equals R on the previous slide. So the way you could think of this is the following. If you have a page I that has 3 outlinks, then at this column that corresponds to page I, you will have 3 non-zero entries, and each of these entries will be 1/3, 1/3. Okay? So now, if you have a vector, and you multiply matrix with that rank vector, what you get, right, for a, let's say, for a given entry j, you will basically take this row, multiply it with this column, and wherever there is a non-zero entry here, this means that some node I points to the node j. So the rank j will be updated by the sum of the ranks appropriately multiplied by 1 of the degree for wherever there is a link. So this is why this is a flow equation, kind of a proof by picture. Okay? So what does this mean? It means that I have my graph from before, I have my flow equations. Here is how now my matrix M would look like. It is essentially the adjacency matrix where the entry is 1 over the out degree. So for example, node M has out degree of 1, and it points to A, so that this entry here equals 1, right? This is this link. Okay? So now I could write this, you know, R equals M times R. I say R, M, R, right? And I have this type of equation to solve. So I will now give you a quick explanation why about this eigenvector formulation of PageRank, right? So I'm saying flow equations can be rewritten as R equals M times R. What this means is that the rank vector R is the eigenvector of the web matrix M, this transformed matrix M. And here is another thing, right? Like we have written this R equals M times R. I could do the following. I could start with some vector u. I could multiply it with m to get my new vector u. I could multiply it with m again to get the new vector, and I would keep multiplying it for a very, very long time. And if I ask what is the vector I would return after I take something and keep multiplying it with m, then what the limiting vector of this thing would be, it would turn out that it would converge to the eigenvector, right? Basically, it would converge to the eigenvector with eigenvalue 1. And, right, so from this point of view, this is now very efficient to solve. All I have to do is I have to take some vector u and then keep multiplying it with m for a very long time. Usually, you know, 50 iterations is enough. And in 50 iterations, this computation will converge to the principal eigenvector. This is the eigenvector that corresponds to eigenvalue to the eigenvalue with value 1. And this is called a power iteration because we are just iterating u times m, and we keep doing that. What I have next is to explain this power iteration a bit more, and then what I have hidden from the presentation but is in your slides is proofs why this works and why does it converge and all that. It's like 3 slides, it's not too hard math, okay? So what is this power iteration method? Power iteration is the following, right? And we talked about power iteration when we talked about SVD, if you remember. There we said, how do you find eigenvalue and the corresponding eigenvector? You can do power iteration. And the idea for our case will be, let's come up with some initialization of rank vector R. Let's call it R0. Let's compute, you know, R0 times M to get R1. If the difference between the two vectors is small, we are done, less than some epsilon. Otherwise, compute this thing again. Take R1 to obtain R2. Again, what's the difference between R1 and R2? If it's less than epsilon, we are done. Otherwise, repeat. And as I said, in about 50 iterations, even over a graph with billions of nodes, this thing will converge, and this will be your PageRank scores. And this is called power iteration. To show you that this works on a simple example, here is my power iteration in the pseudocode, right? I initialize R, and then I run steps 1 and 2 until I converge. So let me now show you. This is again the graph we have. This is our matrix M. This is our initial guess at the PageRank importances. And all I will do is I will take this vector and I will keep multiplying it with that matrix up there in the corner. You know, after first multiplication, this is what I get. After second one, this is what I get, right? So I basically now take this vector, multiply it with M, and I get this one. Now I take this one, multiply it again by M, and I get the next one. I take this one, multiply, and if I keep doing, this is where it will converge, right? So it will be 6 over 15, 6 over 15, and 3 over 15. If you remember, and you can check yourself, these are exactly the numbers that solve this system of equations. Like a few steps before, when I talked about flow formulation, I gave you a solution to this system. And the solution to this system were these numbers. I think I was dividing by 5 because I can, you know, this would be 2 over 5, 2 over 5, 1 over 5, right? So that's what you can do, okay? So this power iteration, where I just start with this vector and repeatedly multiply it with my matrix M up here, will converge to something stationary. So it means it will stop changing. And here is this converging vector. And this converging vector is exactly solution to this system of equations. Yes?
So are you guaranteed that for any such stochastic matrix, you have a eigenvector with eigenvalue 1?
Great question. So the question was, am I guaranteed that this will work for any matrix M? The answer is no, and I will fix it. Yes, you are absolutely correct. So here, it turns out that this graph has some beautiful structure, which I haven't told you yet, where this magic works. So I will explain what the magic is. Okay, so thank you for the question. It's awesome. But don't be alarmed. So before I tell you that, I want to now, so I gave you this idea of the flow formulation. I showed you the power iteration. I showed you how you take the original matrix, normalize it a bit, and now by just multiplying that some random vector with that matrix, all of a sudden we get a solution to some system of equations. It seems quite magical. So I will explain how this works, but before I do that, I want to go and explain what is called the random walk interpretation. So right now, we have this eigenvalue system of equations type interpretation. Now I will give you a different interpretation that mathematically is the same. And this is this RandomSurfer, random walker interpretation that I was talking about before when I was saying, oh, think of the surfer surfing the web. So the way to think of this is, imagine that at some time t, surfer is at page I, right? And then, you know, at time t plus 1, the surfer will follow one of the i's outlinks uniformly at random. So it means a surfer is at the page, looks at all the available outlinks, picks one of them at random, and makes a step. And now his surfer is at the new page, again looks what are the outlinks, and takes one at random, right? So imagine that the surfer is doing this, and right now they just ended up at some page J, sorry, right? And you know, this process will keep running. So let's think of the following. Let's say that P of t is the vector whose ith coordinate is a probability that the surfer is at page I at some time t. Okay, so this is now some vector where every component tells me how likely is the surfer at that web page at this given time. So what I'd like to figure out, right, is how will the pt plus 1 look based on pt. So I want to say, given that I know the probability distribution of the surfer now does one step, how does the probability distribution of the surfer looks now? Notice, as I said, right, this is a vector, so this vector is a probability distribution over the nodes. Okay? So now let's work out if we know where the surfer, if we have a distribution of our belief where the surfer is at time t, where will the surfer be at time t plus 1? Okay? So how do I figure that out? I figure this out by saying, how does the surfer make a step? A surfer makes a step by selecting a link at random and navigating to the target web page. So the way I can think of this is to say the following. You know, what's the probability that the surfer will be at page j. So this means it will be whatever was the probability in previous step that the surfer was at page I1, dividing by the out degree of I1, plus whatever is the probability that the previous step node I was at I2, divided by its out degree, and then plus the probability it was at I3 divided by the out degree of I3. That's the probability that the node is at the surfer is at page j, right? And if you think, what does this mean? This means the following things. It says whatever was the probability distribution in the previous step, so P of t, I multiply that with my transition matrix M to get the probability distribution at the next step. Okay, so this should be clear, right? So what does this mean, right? It means that P at the time t plus 1 is this transition matrix times P of t, meaning the probability distribution at the previous time step, right? And now, what did we compute? Before we said R equals M times R. So this is very much similar, right? So as I'm running this iteration, I'm basically saying that I want the random walker to converge. Basically, if I keep updating this probability long enough, if I keep iterating this, I will converge to some stationary probability distribution, right? So what this means that P of t is a stationary distribution of this random walk, right? This means that from this time on, the probability distribution won't change anymore, right? My belief about where the random walker is will kind of converge or stabilize, right? So what does this mean is, right, that our original formulation R equals M times R is essentially a stationary distribution for a random walk on this graph, right? Where a random walk was specified by this RandomSurfer type process, okay? And here you have the connection. It's a connection between the flow formulation and the eigenvector, and this is the connection with the random walker, RandomSurfer model, where again, solution to this iteration is a stationary distribution of this random walker. Okay, so this is how things come together. Okay, are there questions? So what I said right now is I said a lot and it's important, and I will say it again. What's important is that two different intuitions came together under the same mathematical formulation. One was this flow equations and the eigenvector that corresponds to the leading eigenvalue of this matrix M is equivalent to thinking about the RandomSurfer and the probability distribution of where this RandomSurfer is, and as the surfer makes a step, where it ends up with. And as we iterate this RandomSurfer long enough, basically our belief to where the surfer is converges to this stationary distribution. And the two views of PageRank are equivalent. Okay, that's the essence of what I said. Any questions? Okay, no questions, moving ahead. So now the question is, right, like when do these things exist and are they unique, right? And the central result of, let's say, the theory of random walks, essentially this is the theory of Markov processes, says that, you know, if graphs satisfy certain conditions, then this stationary distribution is unique and eventually will be reached no matter what is the initial probability distribution. So basically what this means is that I can start with my vector R0 to be anything, and if I keep multiplying it with M long enough, it will converge to the stationary distribution, and this distribution will be unique. So whatever I start with, I will always converge to this thing. That's one thing. Another way to think of this is that wherever the random walker starts, after some number of steps, the random walker, our belief about where the random walker is will kind of become stationary. It won't depend on where the random walker started. Okay, so that's the way to look at this. So now what I want to do is go in and talk about what are these certain conditions and properties of this graph that make this work, okay? And what we'll do is we'll now talk about PageRank the way it was formulated by the Google guys, okay? So summary, what did we do is we took this flow formulation. Here we wrote it as a matrix and we solved it using power iteration. Now the question is, does this converge? Does it converge to what we want? Are the results reasonable? So the first thing is, does this converge? It turns out it doesn't converge on all the graphs. Here is one graph, very simple web graph with just two web pages, one pointing to another. I start with some initial vector and I multiply with matrix M. And you see this doesn't converge, right? So A has all the importance, sends it to B. Now B has all the importance, sends it to A and to B and so on, and it oscillates. So it seems all my story doesn't work anymore. So that's the first problem. And then the second problem is even a simpler graph. Here it is, where if I now create a matrix M out of this, and this is my initial vector, right? I start here, A sends all the importance to B, this is here, now B has to send it somewhere, there's no one, so it converges to all zeros. And again, we are disappointed, right? So it seems something is wrong with my theory. And I'll tell you what is wrong. There are two problems with what we were working with so far. First is that web graphs or real graphs can have dead ends. And dead ends are pages that have no outlinks, right? If I go back, node B here is a dead end because when the RandomSurfer comes to B, the RandomSurfer cannot go anywhere. There's no outlink. You get here and you then jump across the cliff or something, right? So this is what we call a dead end, where basically the RandomSurfer gets stuck. They have nowhere to go, right? And such pages without degree 0 cause the importance to leak out of the system. Again, if I go back, what this means here is my importances nicely sum to 1, my importances nicely sum to 1, and now the importance leaks out of the system and importances sum up to 0, right? So I lost magnitude. I lost some importance mass. And then the second problem is what is called spider traps. And spider traps means that all outlinks are within a group. If you think here, right in this graph, this is the dead end, because when the surfer traverses this edge, it basically from here it leaks out of the graph because it has nowhere to go. This is an example of a spider trap. And basically what this means, as soon as the edge from red to green node is traversed, the random walker gets trapped in the spider trap and it will never be able to escape it. So the probability distribution of where the random walker is, it's in this spider trap with probability 1, right? Because as long as the walker walks this graph, eventually it will get in here and it will be trapped and it will stay in there infinitely long, okay? So these are the two problems, right? Basically the spider traps trap the walker who gets infinitely long stuck in these cycles, okay? So going back to my example, but changing it a bit, here I change the graph so that M is now a spider trap. Here is my matrix M right now, and I show you what happens if you do the power iteration over this different graph, right? And as you do the power iteration, notice how importance of node M, this is the node M, how the importance of node M increases or keeps increasing until all the importance is stuck in M. And the way you see this, if you think of the random walker in my example, you keep walking between A and Y as long as you want, but as soon as you get to M, you are stuck in M. So after infinitely long, you say, where is my walker? My walker is in node M with probability 1. And this is kind of unsatisfactory. I don't want M to have all the importance. Y and A are also important. So how do you solve for spider traps? You change your random walker model. And the way the Google guys decided to change it is to invent this notion of a teleport. So your random walker has now two options. At every step, the random walker flips a coin And based on that coin flip beta, the walker makes one of two decisions. Either it follows an outlink at random, which is what we were doing so far, or with the remaining probability, the random walker teleports itself to some random node, right? So this is in some sense, you parachute yourself at some other part of the graph, or you keep walking, okay? Typically, beta is set to be somewhere between 0.8 and 0.9. So 0.85 is kind of the best thing to set, which basically means that the random walker on average makes 5 steps and then teleports, okay? So now, why will this happen with spider traps? Because the random walker can walk, gets into the M, and after a few steps, it will teleport out. So the random walker can always escape with some probability because of the teleportation, right? So the way you can now think is that every node, there is a little kind of outlink out of it that says, oh, if you are here, you can always teleport out yourself from that node. This is what the change does right now, and this fixes our spider trap problem by basically by changing the process and allowing for this teleportation. Yes?
These count as like links with importance. So do we have to go and adjust the importance values for the links for every single node?
Oh, of course now everything will change because now my random walker it's a different process. So I need to change how I define my matrix M. Correct, that's a good point. Okay, so that's the first thing. And then the second thing is, what if I have my dead ends? Like my node M is a dead end, right? So if you look at how the matrix M would look like here, where there is M, there is full of zeros because M has no outlinks. And if you start with doing my power iteration, here is the first vector, and I keep multiplying by M, after a while, it will converge to a vector full of zeros. Because the importance is leaking out of M because the random walker has nowhere to go. That's intuition. What do? I say, if you come to a dead end, you always teleport. So what this means is that for nodes that have the out degree 0, where my matrix M would look like this, now I say, oh, you always teleport. You can teleport to node Y, A, or back to yourself. So basically, I replace this column of zeros with a column of 1 over M. Right? I basically say, whenever you come to M, you can teleport wherever you like, to yourself as well. Okay? So this is now the solution to the problem of dead ends. Okay? Now, why do teleports save both problems? Why do they solve the spider traps? Why do they solve the dead ends? Right? Here is the reason why. Spider traps, right? Spider traps are not a mathematical problem, right? Our convergence and everything still happens. Just PageRank scores are then kind of stupid, right? So we don't want PageRank scores where all the importance is trapped in a spider trap. Because we don't want that, we want our random walker not to get stuck in a spider trap, so we allow the random walker to teleport, so it can always teleport out itself from these spider traps, right? In some finite time. So that is why we don't, why teleports save spider traps. Now dead ends, in some sense, are a problem, because otherwise our power iteration converges to 0, which is also not what we would want, right? The reason why it converges because matrix is not column stochastic anymore, right? We have this column full of zeros, and a column with a lot of zeros or full of zeros doesn't sum to 1, so the matrix is not column stochastic, right? So this means we have to make a matrix column stochastic, and the way we do this is that basically we always teleport out of the node with probability 1. Yes?
It seems like these problems are naturally occurring in the web. What about things that are like adversarial against PageRank?
Great question. What about things that are adversarial against PageRank? Come to the class on Thursday and I tell you. So this will be the topic for Thursday. Okay, exactly. Because you could now imagine I wanna I'm a bad guy. I will change the structure of the web to make my web page look very important, right? And we'll talk about how do you deal with that. But that's exactly what web spammers do. Search engine optimization people, they want the page to be on top, so they will engineer some part of the web to push that page up. Okay, that's a great question. Yes?
If the graph was undirected,
Yeah.
then like we wouldn't have any issues.
If the graph would be undirected, then we have no issues. Exactly, because you can always go back, right? So you cannot get stuck. You cannot fall out of the graph because the edge has no direction, so you can always go back. So this is, if the graph is directed, then you have these problems. If the graph is not directed, random walker is free and happy to roam around as much as it wants. Good question, actually, good observation. Cool, thank you, these are great. So how do you now put all this together, right? We have this random walker formulation where we say with probability beta random walker follows the link at random, and with probability 1 minus beta, it jumps to some random page. This is the paper, 21 years old, I guess. Just got into the, how do you say, maturity. It can get drunk now or whatever, right? So what is it, right? Like, how do we deal with this, right? So we say, what's the score of page J? You say, the score of page J is the probability of random walker being at node I, picking a random link, and navigating to node J. But the random walker does that with probability beta. So that's why we multiply here with beta. And then you say, there is another way for the walker to come to page J. The way that probability is, the random walker decides to jump. Here is the probability of jumping, probability of teleporting. And now if the walker decides to teleport, it must land at node J. There are n nodes in the network, so probability of random walker landing at J is 1 over n, right? And this is now my recursive definition, right? So essentially, I still have my matrix M that I pre-processed to have no dead ends. I have beta here, and then this is the probability mass that comes from the random walker deciding to teleport and landing at this particular node J. Here we are assuming that random walker can land at any node with equal probability. That's why here is 1 over n. Okay? Great. So how can you now write this out, right? Here is my PageRank equation that I said before. And the way you can write this out, it is still a recursive formulation. You can define this matrix A that is beta times matrix M plus 1 minus beta times a dense matrix where all the entries are 1 over n. Okay? And now if this is your matrix A, then the equation above can be simplified into R equals A times R. So what does this mean? This means that power iteration will still work, right? If I formulate this matrix A, then basically my new RandomSurfer, this one with teleports, is still, the solution to it is still eigenvector of this matrix A that has the following structure, which is M scaled by beta plus 1 minus beta, and then a matrix full of 1 over n's, and the size of the matrix is m by n, because n is the number of nodes in my graph. As I said before, how do I usually set beta? I set it to be 0.85. Okay? So let me now give you this, and then I'll comment a bit, right? So here is now my graph. I have a spider trap here. Here is my matrix M. Notice it is column stochastic, right? Columns sum to 1. Now I also, you can think that I almost like add these edges that are there due to the random jumps and teleports, right? So I say now this is 0.8 times M plus 0.2 times matrix full 3 by 3 matrix where every entry is 1 over 3. I add the two together, and here is my matrix A. And now if I do power iteration on my matrix A, here is the starting vector, and I keep multiplying, I get it to converge. The coordinates sum to 1, and these are the importances of the nodes. and these are now the this is the eigenvector corresponding to the eigenvalue 1 of my this transformed matrix A. Okay? So now everything sounds great. There is one huge problem with this. Can somebody tell me what's the problem? Think that I have a graph on 1,000,000 nodes, or maybe 1,000,000,000 nodes. What's the problem? Yes, great. Okay, awesome, thank you. So what's the problem? The problem is that this matrix is a billion times billion, right? So this matrix has 10 to the 18 different entries. So, and every entry is non-zero. So this matrix is huge, right? Not even Google can work with such big matrix. So the question is, what do you do? The point is, we never want to materialize this matrix A because it's dense. And for any graph that is non-trivial in size, I cannot even materialize A, so that then I could run this power iteration on. So we have to do something else. So what we will do is talk about how do I actually go and compute this thing. So far, we just developed the math. How do I compute it? And right, the way we said it was, we will run power iteration over this matrix A. We said how to compute matrix A is, beta times M plus 1 minus beta times this matrix that's full of 1 over 3s. So this means that the sum of these two matrices will also be a full matrix with all the entries being non-zero. And as I said, the problem becomes that, if I have 1 billion pages, I would need basically 1 billion squared number of entries to represent my matrix A. So I cannot do that even if I wish to. So what I will do is the following, right? What we have so far, we want to run this power iteration over this matrix A, where AJI is, beta times MJI plus 1 minus beta over N. That's what my matrix A is. And then I want to run power iteration. I spelled it out there. Now I have this AJI, and I will write it out what it is, right? So I just took the thing above, and I expanded what definition of A is. And what I can do now is I can kind of push the summation in, right? I have here one big summation, and I can distribute summation inside. So I have a sum 1 to n over beta times mji times ri plus, 1 minus beta over n, and then a sum over ri's, right? Because I take that ri and I multiply it in here and I multiply it in there, okay? So now I have taken this one matrix vector product and kind of expanded it out in these two summations. I have a summation here and I have a summation there, right? And now if I try to rewrite this again, what do I notice? I notice that sum over Ri equals to 1, right? The sum of the PageRank scores equals to 1. So this thing disappears, and this summation is still here, okay? So now this is super cool. Why is this super cool? Because I can do my power iteration here, and then I just add this constant term. So essentially what it means is that what we got is that R equals beta times M times R plus 1 over beta divided by N. Okay? So this is now great because I can iterate this equation, and this is just some constant that's the same for all the nodes, and that makes it great, right? So now we have rearranged our power iteration, and the trick here is that my matrix M is sparse, right? The number of non-zero elements of M is the number of links in the graph. Multiplying by a constant just changes the values, doesn't add new entries. This is the vector, and that's that constant term, right? So real graphs are sparse, so this will work really well. So all I need to do is in every iteration, I need to say R old. I take the old version of R, multiply by M, multiply by beta, I get the new R. And then I need to add a constant of 1 minus beta over n to every entry in this R new. And I just keep iterating, right? And this will nicely converge. So this is really the PageRank algorithm, right? It's like I do this plus 1 over beta, and then I keep iterating, okay? Here is now the full PageRank algorithm where I initialize my R, I will call it R old, then I go for every node J, I say what are the importances of its people that point to it, I sum them up, divide by the out degree, multiply by beta, and this is now the new R. And then what do I need to do is now I need to go and insert the leaked PageRank. So rather than adding, like we said here, beta minus 1 over n to every entry, I will actually do the following. I will say, what is the sum of the new PageRank scores? And whatever is missing to sum up to 1, I will add 1 over n of that to every node. So this means that here I'm inserting whatever the PageRank leaked, either due to random jumps or due to dead ends. So this formulation allows you to deal with dead ends, right? So in my previous slide, I assumed there are no dead ends. And if there are no dead ends, then the value of this term would be 1 minus beta over n. But if there are dead ends, then all I do is this is basically beta times m times r. Whatever I get here, I compute the sum of it. And whatever I'm missing between this sum and the value of 1, that I insert back, right? S is a value between 0 and 1. Whatever is the difference between 1 and s, I divide by n, by the total number of nodes, and everyone gets an equal share of this difference, right? This is how you would implement the PageRank algorithm in practice, okay? And as I said, there is a bit of non-triviality here, because here I'm assuming also that there might be dead ends in the graph. Okay, are there any questions? Yes, great. How do I take care of the spider trap? So there is still this constant term that I'm adding in, and this is the effect of the random walker teleporting out of the spider trap, right? So the teleportations take care of the spider trap. And I just showed you on the previous slide, right, how to deal with teleportations. You get this constant factor that you add to the node because somebody might land to it because of the teleportation. And it doesn't matter where the node teleports from. You just care that it lands at your place. And that's it. Okay? Good question. Great. Anything else? Right, so here the view is different, right? I'm asking, how do I get to the node? Before we said, I am at a node, how do I get out? Now I'm saying, how do I get in? And the way I say, how do I get in is by either navigating from a neighbor or because I jumped to it. And if I jump to it, I must have jumped somewhere out. And that's it. Good. Any other thoughts, questions, doubts? Okay. So now so here is the algorithm, and if your graph fits into memory, this is how you would compute these things. Now, what about if your graph doesn't necessarily fit into memory, right? How does Google do this on billions or trillions of pages, right? There must be a scalable way to do this, right? So the idea is that what you can do is you can pre-process your adjacency matrix in this type of format, where you say I have the source node, I have the degree, and then I have the IDs of the destination nodes, right? And then I have next node, out degree, and then I have the out degree number of numbers, because these are now the IDs of the target nodes, and so on and so forth. And this is now my matrix in this sparse form, where this is a row, and then this is the number of non-zero entries in that row, and here are the entries. That's one way to think of this. So imagine I can fit the entire vector R new into memory. So at least I'm able to fit R new into memory. And imagine I store R old and matrix M on the disk. So then what I could do is the following. I could initialize R new, and then for every page with some out degree, I read in the page, the degree, and a set of its destinations, plus the R old at that coordinate. And then for all of the destinations, I say R new at that destination is R old times beta divided by the out degree of that node I, right? So notice here, what is elegant about this algorithm, that the only thing I need to store in memory is this R new, right? So I basically say, I will read one line from the disk, I will read this entry, 0, and this says that node with degree 0 gives importance to 3 nodes, 1, 5, and 6. So I take this entry 0, whatever is the value, divided by 3 here, and I update now entries 1, 5, and 6, right? And then I would load in the next node and the corresponding entry at index 1, so this one, and then I would update this particular entries of, this vector, right? And what is the elegant thing here is that I'm essentially only have to keep this in memory because I'm only doing random accesses here. I can read this sequentially, and I can read this sequentially as well, kind of in parallel, right? So that's how I can do this where I need very little memory. I only need one float per web page. Everything else I can keep on disk and just sequentially read, right? So let's analyze this case. So I'm assuming I have enough RAM to fit R new into memory. And each iteration, what do I need to do? I need to read through R old and M, and then write R new to disk, so that once I write it to disk, R new becomes R old, and I can repeat the process, right? If I say now what is cost per iteration of power method, cost I'm measuring here in how much do I have to read or write from disk. I have to read the vector R once and write it once, so I have 2 times size of R, and I have to read the matrix M, and the cost of that is the number of non-zero elements of matrix M. Okay? So this is the cost, right? It's linear in the size of the data and linear in the linear in the number of edges and linear in the number of nodes. And what is the memory consumption? It's only all I have to do is keep this R new in memory. So it's amazingly cheap, right? So this is clear? This side is happy, that side, great. Okay, so this is clear. What now if I have so little memory? What if I want to compute a page rank of a billion node graph on, I don't know, my cell phone? Actually, I could do it, but not on a cell phone, on my calculator, right? Where even my R new doesn't fit in the memory of the calculator, but calculator comes with a hard disk, okay? So I have this fancy calculator with a hard disk, and I want to compute R new, okay? So how would I do this? One way is, this is called block-based update. And the way you could do this is the following, is you'd say, if I can only store a chunk of R new in memory, then what I can do is I can scan through the matrix M, but in one pass over M and the R old, I will only update 0 and 1, whatever I can store in memory, right? So basically what this means is that I break my R new into blocks, and I only keep one block in memory, and then I make a pass to only update that block. And then I would flush the first block of R new on disk. I would load the second block of R new, and then I would have to make another pass over M to update 2 and 3. And now that I have updated 2 and 3, I would flush it, and I would come back to load the next block of R new, and again make one pass over the data. So what would be the total cost? If I take R new and break it into k blocks, then it means I need to scan over R and M k times, right? So my cost would be k times loading M and R and writing R back to the disk, right? So my total cost would be k times M plus k plus 1 times R, right? Basically, because M is so big, right? M is much bigger than R. In some sense, what is expensive, the constant here, is much bigger than this value, right? So really, what I want to minimize is number of passes over this guy. And this guy is much smaller, so I don't care so much about it, right? So M is, let's say, 20, 30, 50 times bigger than R, okay? So here's now how I could lay out data to be even smarter. And the way I would, and this is now called the block stripe update. And the way this works is that I took my adjacency matrix, but I also partitioned the adjacency matrix, right? So let me go back, explain. So before I had my matrix, but I only partitioned R into these blocks, right? And the idea was that I load one block of R and do one pass over this to update that block. And then I take new block and another pass over to make the update, and so on. Now I will also change the layout of matrix M. So let me show you how to do that, right? So I will store my matrix as 3 separate matrices. And what I really did is I took this destination lists and I partitioned them into stripes, as it is called, right? So what does this mean now? It means that I partitioned the M such that here the destinations are only destinations to the nodes in the first block. And here the destinations are only destinations to nodes in the second block. And here are only destinations to the nodes in the third block, right? So now this means I load the first block of R new, and then I make one pass over the first stripe of matrix M. And then I dump the block and I load the new block. And then all I have to do is make the pass over this stripe. And then I load the next block and make the pass over this stripe, right? So what essentially we did, if I go back, what we did is we took these destinations and kind of partitioned them further so that when I'm updating that block, I don't even need to read this node or that number 5 because they are meant to update something else, right? And when I'm reading the first line here, I know I can skip 3 and 5 because all I care about is updating 0 and 1, okay? So that's what this block striping algorithm allows me to do. Basically, it allows me, I change the structure of my matrix M to partition it in these stripes so that when I update the blocks, I only read the relevant part of matrix M. So let me show you the analysis. How long does this take, right? The way this takes, it's actually very fast, right? I'm reading my matrix M in only once, right? If I go back, I'm reading, I make one pass over the matrix M. Of course, this part is saved multiple times. So I have a bit of overhead because it's a bit of duplication. But in terms of edges, each edge gets read in only once, right? So if I do this, the cost is the size of M plus this is the number of blocks, k plus 1 times R, right? Because if I go back, the reason for that is I need to read the stripe and the entire vector R old to update this guy. And then I load in the next block. I need to read the next stripe plus the entire of vector R old to update it, right? So if I have k stripes and k blocks, I need to read this guy k times. I need to read this once, and I need to dump this back on the disk once. So the total computation cost is here, okay? So this is how you could do this and how you would really implement this on graphs that are super huge, right? And you can do this on Hadoop and so on. So essentially, yeah, Hadoop was in some sense developed or invented also because of this type of applications. This was one of the motivating applications that kind of Google wanted to do but couldn't do before they invented MapReduce. Right? They used specialized systems and then they realized they're just kind of gathering information from neighbors. So now I want to finish with a bit of high-level remarks and then we are done. So PageRank, right? The idea was that it measures some kind of popularity or importance of a page on the web. And it is based on this idea of random walker. One thing we did in our random walker and teleportations, we said when the random walker teleports, it can land wherever they want. The probability of landing is uniform. But you can actually go and play with where the random walker is going to land. And you can make that landing probability non-uniform as well. And that non-uniform landing probability is called topic-specific PageRank. So this is what we'll talk about next. There are other measures of web page importance that are not only PageRank, but are kind of similar formulations. One of them is called hubs and authorities. Another one is called salsa. So there are two competing algorithms that were kind of developed later. And as there was a good question before, this formulation is susceptible to what is called link spam, where basically somebody can come and create an artificial topology of hyperlinks with the goal to increase the PageRank score of a single page. And on Thursday, we will talk about this method called trust rank that tries to identify these artificial topologies that are there just to boost importance of a single page. So this is kind of the plan for Thursday. I was also told by Michele, but I forgot to say this at the beginning of the lecture. Thank you for submitting homeworks. New homework is due on Thursday. Please submit code, right? Don't forget to submit code. You have to submit all your code. If it says 3 times, you have to submit it. Even if it only says once that you have to submit it, you still have to submit it. And even if we say that we forget to tell you to submit it, you still have to submit it. Okay, so don't forget to submit your code. Be careful, read the homework problem, but submit us your code. I'm happy to take questions, otherwise we can be done with the class. Great.
Can you talk again about why the R vector necessarily converges after mixed iteration?
Great.
Like, is there proof for that?
So why does the vector R converge after many iterations? The reason for that is because our matrix is column stochastic. If you open the book or if you open the slides, you will find the proof in the slides. Okay, let's finish here. Thank you very much.